Hello class, we're about to start section 5.4, using a power property with exponential models. Example 1. We all know it is dangerous to eat perishable food that has been left unrefrigerated. The average time for a bacterium to replicate itself and split into two bacteria is 20 minutes. Suppose there are 100 bacteria on a piece of meat left at room temperature. Working by hand, find the exponential model for the number of bacteria after t hours. So we will have f of t is equal to, we know the exponential model is ab to the x, but since we're using t, we'll use ab to the t. So we will have f of t is equal to, remember we have 100 bacteria that we're starting off with, so that will replace a. So we'll have 100 times b to the t power. Now, remember it says that every 20 minutes it doubles. So after 20 minutes, it would double from this 100 to be 200. So 200 would equal 100 times b to the t power. So now we would divide each side by 100. And we'll have 2 is equal to b to the t. Now, what we will have here, we need to find out what t is equal to. Now remember it says t hours, but we're basing this off of 20 minutes. So we need to go off to the side and see how much is 20 minutes of an hour. So we know an hour has 60 minutes. So 20 divided by 60 is the same as 1/3. So our t here is 1/3. So we would end up with 2 is equal to b to the 1/3 to replace the t. Now, we need to get rid of this 1/3, and we do that by taking each side by the reciprocal of this power. So we'll take each side to the third power. Now, 2 to the third power is 8, which is equal to b. So our final answer is f of t is equal to 100 times 8 to the t power. And that is our formula. Now, we scroll down here to b. It says, what is the base b of the model and what does it mean in this situation? Now, we already discovered that b was equal to 8. So, now we would make this into a percentage. So we have b is equal to 800% minus 100%. Which gives us 700%. We learned this in the last chapter. This was from section 4.5, your notes from section 4.5. So we have 700%. So what this is saying is every hour, the number of bacteria on this meat increases by 700%. And that is our final answer for B. Now, what we need to do next is go here to C. Now, C states that at this rate, how long will it take 100 bacteria to grow to 1 million bacteria? So what we would do, we would take that same formula. We would have f of t is equal to 100 times 8 of t. And we would substitute in f of t to be 1 million equals 100 times 8 to the t power. We divide each side by 100. And that would leave us 10,000 is equal to 8 to the t power. Now, we'll take the log of both sides. So we have a log of 10,000 is equal to log of 8 to the t. Now, of course, we move the t out front, which we learned in the last lesson, which was section 5.3. So we have t times log of 8. Now we'll divide each side by log 8. Now, Log 10,000 divided by log 8 will give us approximately 4.23 hours. Is approximately equal to t. And that is our final answer. Now on your sheet, you have what is called a frame of reference after this problem. So I'm going to read it to you, even though it's not shown on my sheet here. It says, frame of reference. There are typically 1 million bacteria cells in 1 cc of fresh water and about 40 million in 1 gram of topsoil. Each bacteria cell is around 1 micrometer in length, longest dimension, weighing about 10 to the negative 13 power, and can have doubling rates as quick as 10 minutes. Now, we need to move on down here to example 2. It says the nuclear disaster at Chernobyl, Ukraine in 1986 released large amounts of radioactive materials into the environment. One of the most dangerous of these was cesium-137, which has a half-life of 30 years. Now, working by hand, find an exponential model for the percent of cesium-137 remaining at T years after 1986. So if you look here, it says it has a half-life of 30 years. So we know we're going to go, as far as our T is concerned, our T would be 30 years, because this would be 30 years after 1986, which we all know 30 years after 1986 is 2016. So now we'll write our formula. We have C of T is equal to, now we know we will have AB to the T. So we have C of T is equal to, now it tells us here that we would start off with 100% at the start of this. So our A would be 100. Now, and it'll be B to the 30th power because we found out what T was. So we'll have 100B to the 30th power. Now, we're going to divide, well, first of all, C of T we know is equal to, now backing up just a little bit. Now remember, our first year we would have 100%, or we would just put 100 here. Now, remember our C of T is the half-life. So our C of T would be 50, because 50 is half of 100. So we have 50 is equal to 100 times B to the 30th power. Now we would divide each side by 100, and we would have 1/2 is equal to B to the 30th power. Now we need to get rid of this 30th power. Now we could take the 30th root on both sides. The 30th root of 1/2 and the 30th root of B to the 30th power. And that would give us approximately, B would be approximately 0.9772. So our C of T would be equal to 100 times 0.9772 to the T power. And that will be our equation. Now we scroll down here to B. It says, what is the base B of the model and what does it mean in this situation? Now we know our base is approximately 0.9772. So we will have to take this value, first of all, make it into a percent, which is 97.72%, and subtract 100%. And remember, this goes back to less than 4.5, and this will give us a negative 2.28%. So this means every year, the percent of cesium-137 decreases by 2.28%. Now remember, that's a negative 137 here. And this here is our final answer. So it's a 2.28%. Okay, so now it says C. How long will it take for the amount of radioactive cesium-137 left in the environment to be 10% of the amount released in the disaster? So we would have, we know we would write 10 is equal to 100, and then in parentheses we'll write 0.9772 to the t, and we will have to divide each side by 100. So this will give us 0.1 is equal to 0.9772 to the t power. Now we would take log of both sides. Oh, actually, this is supposed to be 7, not a 9. So it's supposed to be 0.9772. That was a mistake. Okay, so now to the t, so we will have log of 0.1 is equal to, we will bring the t out front, t of log 0.9772, and then we would divide each side by the log of 0.9772. And then we would end up with t would be 99.8 years. Now remember, this is since 1986, so we know that's about 100 years. So the year would be about 2086. Okay, now we will scroll on to the next page where we come here to example 3. It says the speed of a computer depends in part on part of the chip speed. As technology advances, faster chips have been produced. Now we look here at A. It says let C equals f of t be an exponential model for the chip speed at t years after 1970. Find the regression model that fits the data to 3 decimal places. Now, to expedite a little time, I just put down what these values are. Remember, these are years after 1970, so we would make this our t, which would be for 1974, that's 4 years after, and I listed all of how many years after these years are. So that would be our L1. Our L2, we know, would be our chip speed. So we will put this in as if we're doing linear regression, but you know we're doing exponential regression. So you would go through, press your stat, go to calculate, and then you would go down to 0, which is exponential regression, and it would give you this formula here. Now let me restate that. First you would type in your L1 and L2, just like you would do with linear regression. But then after you type these in, you have to press your stat, then go to calculate, and then go down to 0 where it says exponential regression, and it will give you this formula here. And that will be your final answer for A. Now we go down here to B. It says, what is the base of the model and what does it mean in this situation? Now we know the B here is equal to 1.256. And if we write that as a percent, we have 125.6% minus 100%, which will leave us 25.6%, which means that every year microchip speeds are getting faster by 25.6%. And that is your final answer. Now we have C. Use your model to predict the year during which the chip speed reaches 10,000 megahertz by hand. So we know that our f of t would be 10,000, and it equals to, it'd be 0.633 times 1.256 to the t power. Now we'll divide each side by 0.633. And that will give us